Welcome to the week number 7, in which we'll investigate one of the nicest systems out there, structural systems that we engineers use to build from bridges to telecommunication towers, and then everything in between. So this topic is dedicated to trusses, and we'll study methods to solve them. What is the solution? What is the solution of a truss? Well, it involves the calculation of the reactions of the truss and the calculation of the internal forces in the members, right? But first of all, what is a truss, right? What is a truss, and where can you find these trusses? The truss is one of the most commonly used types of structural systems. Consists of a number of straight struts or bars joined only at the ends. Now, the short kind of a shorthand for a truss is that it is composed by one of the strongest and more stable shapes on Earth, right? The triangle, right? So you will see that a truss is made by many triangles, right? And then once I give you, for example, some of the pictures, you'll see that you indeed have seen many trusses in your life. Now, trusses are commonly used for lightweight construction over long spans, right? So they are very strong and very lightweight, right? And this is the kind of the basic shape they have. Trusses can be thought as a collection of members, right? And then they are saying that this is a member, right? This is another member, right? This is another one, and this is another one, and this is another one, right? Collection of members that meet at something called joints, right? So this is a joint, right? Where two or more members meet, right? We call those joints, right? Joints. And then we are interested, right? So solving a truss, right, consists of determining the magnitude and sense of the force in each member, right? Now, a spoiler alert, right? Truss members can only be in tension or compression, right? These are the two possible states. So you want to find if they are in tension or in compression and how much force they have, right? So how much tension, how much compression, right? That's the main thing you want to know about a truss. Now, depending on the amount of tension or compression the truss have, right? An engineer will have, right? They may say, you know what, we need a piece of steel that is 5 centimeters, right, in the sides, right, depending on the tension or the compression, or maybe it's 10, right? Maybe it's 10 centimeters, or maybe it's not made of steel, right? Maybe it's made of wood, or maybe it's made of another material. So an engineer, an architect will need the force in the members to start deciding about the material that they are going to make that truss of, or the dimensions, right? And then to solve for these forces, we will use equilibrium conditions, right? And a few simplifying assumptions. Now, all the tools that we'll use to solve for trusses, or to solve trusses, these are tools that we already cover, right? So the beauty of it is that we will see the application of these tools. Now, just to kind of warm your hearts towards trusses, right? You will see that trusses are quite a common tool, right? Used by everyone, right? From civil engineers to mechanical engineers and aerospatial engineers, right? A truss is such a powerful shape. So a truss, right? It's that the basic shape is a triangle, right? So you see that roughly they make a triangle here, right? And there are many triangles in between, and even these small parts, right? You can see that there are small triangles in there, right? Some of the most iconic bridges around the world are made of trusses. You see the triangles here. on all these structures, and then not only for bridges, but also for the skeleton, right, of cars, and in this application of racing cars, they want something that it's very lightweight and very strong, right? So it's no coincidence that they choose trusses to serve this purpose, right? And then this shape, right? This shape is not secret, right? So from many years ago, right, these different type of trusses were being used for different purposes, right? For train bridges for trains, right, such as this one. Now cars, right? If you live in a house, right, in Edmonton, for example, or in Canada, chances are, right, your house is made of wood, and all the roof, right, all the roof is made with wood trusses, right, wood trusses such as this one, right? Now, the geometry of the truss and all these details depends on the amount of force you want to carry, right? You want to carry. It's no, I mean, these shapes don't just come because we propose something. No, there is a mathematical basis for it, right? And many of the methods that we'll discuss two basic methods. They can serve you to investigate trusses even in 3D with a few simplifying assumptions, right? So it will be quite powerful, right? It will be quite powerful. So we have different types of trusses, right? 2D and 3D, right? 2D trusses, all the members lie in one plane, right? All of the members lie in one plane. Now it's really difficult to find a 2D truss in a real application, right? Usually you would have a 3D truss, right? But under some simplifying assumptions, you can find plenty of 2D trusses, right? Even in 3D structures. For example, you may have a truss such as this one, right? And then joined to another truss, right, which has the same geometry. And then you can of course say that these two trusses carry the same weight, and you can take this truss and analyze as a plain truss, and take the one in the back and analyze as a plain truss as well. So even in cases in which you have 3D trusses, there are many of them that can be analyzed as a 2D truss. So, and then of course there are space trusses, right, such as the ones used in cranes, such as this one. So this, for example, is a space truss that is being used to push this bridge, right, and to carry it to the next span, right? So three-dimensional trusses such as this one, right? Of course, quite common. And then the assumptions we use to analyze trusses, right, is that all the loads act at the joint, right? In real life, this is often true. This is often true, right? And the point is that we want all these forces to act at the joints in this way, right? So we will have supports in our truss, right? And what we want is that whatever forces are coming to the truss, they are applied at the joints, right? This is right? This is necessary for our assumptions to work, and the procedures we're going to study to work as well, right? In the case in which some of these forces act at a position different from the joints, then our theory breaks down, right? So those cases cannot be analyzed with the tools we are going to see in this topic. So most applications in real life have the loads placed at discrete locations at the joints, right? Because that allow engineers to make simplifying assumptions about the behavior of these members. One very important part of the role of an engineer is actually not make things difficult, right? It could be very well that an engineer can design a truss that can have a load in the middle, right? But it will make the analysis quite complex, right? So we don't design actually complex things just because, right? if we can have the load acting at the joint, so much better, right? So much better. So, right, we can have examples for a bridge, right, in which the loads from the deck, right, the deck is where you have the cars, right, you have the cars circulating, right. The deck is supported at discrete locations, right, just at the joints, right. That's where it touches the truss. So actually, that transfer of load happens at the joints in the way that it should be, right, in other applications, right. So we design these load transfer points to coincide with the joints in the truss, right. We do that on purpose, right. We do that on purpose. So, for example, you see here that this is a railroad bridge, right? And then at the point, right, these are the joints here, right? These are the joints. And at these discrete points, right, is where the actual railroad, right, is actually being supported onto the truss, right? So from long time ago, people were aware of the need of having these sort of assumptions, right? So all the loads act at the joints, right? All of these loads act at the joints, and it's the same for a roof in which you are using a truss, right? You would support the ceiling or the roof, right, at discrete locations at the joint, right? So true in all these applications, right? So it says that in order to solve for a truss, right, we approximate equivalent joint loads, right, and then check for the combined truss and beam action of the members at the later stage in the design. So this essentially is talking about a situation in which you can have the roof just supported on the truss, right, not at a discrete location, but all along this member, right? So you can have snow here, and then you may actually be loading on not at the joint but just at this top member. So it says that this paragraph says that you can still make an assumption, right, or start the analysis thinking that the loads act at the joints, but that assumption needs to be checked at a later stage, right? So it's quite complex to do that. Essentially, the recommendation is that that all the loads should be at the joints, right? Now, the second very important assumption, right, is that all joints act as pin connections. Now, we have talked about pins, right? We have also called them hinges, right? We have said that a hinge, right, can transmit translational reactions, right, but allows rotation, right? Allows rotation. So this is allowed, and this is prevented, and this is prevented. So in the case of a truss, right, in the case of a truss, they are saying that a given joint, right, a given joint acts as a hinge, so it cannot develop moment, right? It cannot develop moment, so it has to, or it allows rotation easily, right? Now in real life, right, a real connection looks like this, right? Now if I ask you to tell me, okay, does this resemble an actual pin, right? Do you see these elements rotating about the middle point of this connection? You may actually, I can see you thinking, well, you know what, that is not a pin, right? That is not a pin because I cannot see those elements rotating. Well, these connections actually, right, these connections, the members are typically very small, right, in size. And these connections are not very effective. So you have a little bit of rotation on the members. But you know what? Even a little bit of rotation releases enough moment so that they can be considered as a hinge. So even though we don't detail connections as a specific hinge, right, or as a perfect hinge, you still, with good accuracy, you can assume that the joints indeed act as pin connection, right? As pin connection. So even though a real pin will have some restraint against rotation, right? If you look at a realistic detail for a truss, these connections will release the moment through a little bit of rotation, right? But that's enough to release the moment. So we can still assumption, right? We can still assume that these connections act like a pin, right? The effects of the rotational restraint are negligible, right? So this rotation happens, right? This rotation happens. Now, this also brings to attention the fact that you see all these members arriving to the same joint, right? So if I take equilibrium, right, if I make a free body diagram of the joint, right, and I see a bunch of forces that are concurrent to the node, right, can I have movement, right? Can I have movement on that node? Well, these forces cannot apply moment, right? So if I make the free body diagram of that connection, right, I see that there is no moment to be created on the pin, right? There is no moment to be created. So that is something really nice, right? The moment that could arrive to that pin, it's impossible because all these points are collinear, right? Are collinear. So it's good, right? Double whammy. We cannot develop a moment, and we cannot transfer moment because the forces are collinear, right? Now, if we take all these assumptions together, right, the conclusion is that these members, the members of a truss, are two force members, right? Two force members. So these guys can only carry either compression or tension, right? Either compression or tension. And this is the explanation, right? This is the explanation of why. So you can have forces, right, at the nodes on a given member, right? But if you resolve these forces into a resultant, you will see that you have the same force acting on the same line of action, right? It could be tension, or it could be compression, right? And that's it. That's it. A truss element can only carry tension or compression. Now, if you are going to build a simple truss, right? A simple truss with pins, with actual pins. Like, let's say you have 4 members, and you want to develop a truss. So once you apply load like this, you can see this actually, right, deforming this way and then falling, right? So this is an unstable truss, right? This system will collapse. What you need, right, is the triangular shape. So you need a member there to make the system stable, right? So careful, you need that triangle, right? For stability, right, all the basic shapes within the truss must be triangles. And then there is simple rules to know if a truss is going to collapse, right? So there is a basic equation here, right? A basic equation, which is 2 times n, right, minus the number of members is equal to 3, right? So if we have this equation, right, let's see what happens when we evaluate that simple equation for the structure that we saw collapsing and the structure that we saw that it was stable. So n is the number of joints, and m is the number of members, right? So let's apply the equation to this. This one, we know that it collapses, right? So 2 times the joint. So I see 1, 2, 3, 4 joints. So 4 joints. And then 1, 2, 3, 4 members. So 2 times 4 gives me 8, minus 4 gives me 4, right? So if you have 2 times n minus m bigger than 3, the structure is unstable, right? Structure is unstable. So this structure will collapse, right? So here we don't meet the equation. We have it actually bigger than 3, so the structure is stable, right? Now, if the equation is equal to 3, is actually stable. So for example, this one I see 1, 2, 3, 4 nodes, right? So 2 times 4 minus the number of members, 1, 2, 3, 4, 5. So 8 minus 5 is equal to 3, right? So we have what it's called like a simple truss. The more technical name is statically determinate. It means that just applying the simple equilibrium equations, I can find the forces in the members. And what happens if, right? What happens if 2 times n minus m is actually less than 3? Well, you have a redundant truss, right? Redundant truss. This is statically indeterminate. Now, these statically indeterminate trusses, right, are actually very, very stable, right? Very, very stable, right? They cannot be solved by using the simple 3 equilibrium equations. We need a bit more equations that you will get in a later course. But they are difficult to solve, right? So as an engineer, you have to balance, right? You have to balance. Well, this is very stable, right? Lots of paths for the load to travel, but it's difficult to analyze. And when things are difficult to analyze, people may make mistakes. So sometimes it's easier, or no, it's better to have, right, something that it's simple, such as this case, when 2 times n minus m equal to 3, something which is simple, because the forces can be obtained very easily and you can check the forces, rather than having something that it's statically indeterminate, less than 3, right? And then these are difficult to analyze, right? Difficult to analyze. Very stable though. Right? This is stable and simple. Right? This is very stable, right? But difficult to analyze, right? And of course, you don't want to use. You don't want to do this. This is unstable, right? Right. So a few examples, right? About this. This is the case in which I have a statically indeterminate truss, right? So in this case, right, the statically indeterminate truss, it's also a very important type of truss, right? It's very stable, right? It has lots of paths for the load to travel, right? You see that they added the triangular point, but they added another member, right? So, and then it says that in this case, we cannot determine the member forces by statics alone, right? Now, the good news is that you will learn about these cases in future engineering courses, right? So, there are two main methods to analyze a truss, right? To solve a truss. And what again is solving a truss? Well, finding the forces in the members. And the two methods are the method of joints and the method of sections, right? And then we'll investigate this first, and then this next, right? So things that we have learned so far is that a truss, right, is quite a stable structure that in which we assume that the loads are act at the nodes, right? We're very close to it. There may be cases in which they are not, right? But we have to be careful about those cases. The forces, right, in a given joint, right? The members arrive to the joint, and you have collinear forces, which means that you don't have a moment on those joints, right? On those joints, there is no moment to be developed there. Also, on the way that you build a real truss, right, with gusset plates, right? These connections are a bit flexible, right? And they allow rotation. And then just with a little bit of rotation that you have, you release moment, right? So these are two reasons why in a joint, right? In a joint, I cannot have, or I don't have, or I assume that I don't have a moment, right? We saw that there are different arrangements of members in joints, right? We saw that if n is the number of joints and m is the number of members of bars, right? 2 times n minus m less than 3, right? This is what we have, what we call a statically indeterminate truss. Very stable, difficult to analyze. If we have 2n minus m equal to 3, we have a statically determinate truss. Stable and easy to analyze. And then 2n minus m bigger than 3 is unstable. Right? So these trusses don't stand, right? Cannot resist any load. So this is it. And then in the next video, we will focus on the method of joints, right? And then it's nothing else than applying the equilibrium equations. At the nodes. Which ones? Sum of forces in x equal to 0, sum of forces in y equal to 0, and what about sum of moments? Well, in this particular case, we cannot use that equation because we are investigating a given joint, right? It doesn't develop any moments. So we have only 2 equilibrium equations, right, that we can use at each node. Right? So thank you very much and see you on the other side.